Hello and welcome everyone. I'll start with a brief introduction to Connexus and go over a few housekeeping items before we get going on the presentation. For those of you who are unfamiliar with Connexus, we are a process safety consulting engineering company that provides technical safety services for new and existing facilities. We provide a full complement of training, consulting engineering services, and technical software. To learn more about our products and services, please visit Connexus.com for more information, or feel free to reach out to me personally if you like. Our goal is to do one of these webinars per month, so please consider subscribing to our newsletter on the Connexus website, Connexus.com, so you're up to date on timing and subject matter of future webinars. We also post webinar and other important information on our LinkedIn page, so please consider following us on LinkedIn as well. Also, so you're aware, this webinar is being recorded today, and it will be available for viewing on Connexus.com by the end of this week or early next week. We will advise when it's ready with a LinkedIn post and on our website. We try to keep these webinars as a conversational format, so if you have any questions along the way, please feel free to speak up, or if you prefer, type your question into the meeting chat. We want to ensure we get all your questions answered for you. Today's webinar is a bit of a different format for us in that we've coordinated with the manufacturer of an important and often underutilized safeguard. So joining us today is Jenny Vance with Sofis to help us understand what captive key interlocks are and how they work, as well as some real-world applications. After that, we'll turn things over to the president of Connexus, Ed Marzell, to discuss how to account for captive key interlocks in a PHA LOPA scenario for the typical oil and gas application of pig launcher valve sequencing. With that, I'll turn it over to today's guest presenter, Jenny Vance of Sofis. Take it away, Jenny.
Thanks so much for that welcome, Chris. So we are going to do something that has worked for us in the past, especially during the COVID era. And you should be seeing a presentation right now. Can everyone? Yep. Great. So I've also joined on my phone, and you should be able to see a live video under my name.
Yes, you click on me. That also.
Great. So what we're going to do is I'm going to take you guys through this PowerPoint, and then we'll get to a fun part of the show, and I'll do a live demo with some equipment that we have here in our Spring headquarters. So that's Spring, Texas. That's our U.S. headquarters. And if you feel so inclined, you can click on my name. I might even highlight myself. I don't know. And you can watch that live demo as well. So without further ado, we will get started on captive key technology and drive systems. And just an introduction to what Sofis does and where we fit into a LOPA study of a process. So I'm sure that we are all familiar with these two kind of diagrams, right? We've all seen a process hazard analysis, and we've all seen LOPA risk matrices. So I like to show this as an example. So we typically start where captive keys enter the conversation, starting with a process hazard analysis. And here we are doing a process hazard analysis on an ethylene treater regen system. We've identified that misdirected flow, yes, I know it's misspelled, is something that we want to avoid. And the cause of that misdirected flow stems from an inadvertent opening of block valves. And so now that we've identified this cause, we go down and we say, how often could that happen? We've identified it could happen 1 times 10 to the negative 4th. And so we need 4 IPLs or independent protection layers to mitigate that risk back to an acceptable risk level for our organization. So you go forward and you evaluate different mitigation strategies. And what this example shows is that a trapped key interlock or a captive key interlock is treated as twice as effective as other IPLs. So what that means in practice is that I've just chosen 1 times 10 to the negative third. If your current process is at this risk level, if you add a captive key system, you've now mitigated it down to an acceptable risk level without doing anything else. So why is captive key such an effective process safety tool? Well, it's not just because we say so. Sofis actually had nothing to do with this. But because captive keys function as both an engineering control, working to isolate workers from the hazard physically, and an administrative control, meaning that they show some procedural aspects and they walk workers through complicated procedures, it functions as 2 independent layers of protection. Furthermore, the guidelines for initiating events in a layer of protection analysis, which is a publication that is widely available and published by the Center for Chemical Process Safety, a body governed under the American Institute for Chemical Engineering, has put together some statistics and calculated the generic probability of failure for use in a fault tree diagram scenario. And this PFD is 0.01, which again is 100 times risk reduction. So that's a lot of math, a lot of talking. What does this really mean? And what is captive key technology? So I don't know how many people on this call are familiar with captive keys or what they do, how they look, but I will attempt to highlight my video and see if, does that spotlight work?
I'm seeing it up in the top left corner of my screen. Hopefully everyone else is also.
Okay, if you can go to the top left corner of your screen or wherever you see 2 yellow boxes and click on it, that might be easier for you to see. Hey guys. All right, so what we have here are 2 demo locks in a sequence. This is our captive key interlock here. Here's our actuator. We have a 1/4 turn valve. We have a multi-turn valve here, and these are our example valves that we're mounted on. So as you can see, we've got a red key here, this valve, and we can all agree that this valve is locked in position. It's not going anywhere. Okay. This valve, on the other hand, we could freely do, well, this valve has 2 keys in it, and we can freely actuate this. So the way this works in practice in the field is you start with a starter key. You hand this to your operator, they withdraw it from the key cabinet, and you walk out and you match up your start key to the nameplate here. So this will match. It will tell you what procedure you're doing. You insert your captive key. It only goes into one side of one valve, and you actuate your valve. Now, once you've gotten that valve completely open, you can withdraw your changeover key, typically yellow. Now, I want to point out that this is the only time 2 keys or a key will go into 2 different valves. You match this over into the correct slot. You insert it. Now I can turn this valve. And if I were to turn this all the way over, I would be able to, once I complete turning this valve, I'll be able to retrieve this key, which is locked right now. And now that I've withdrawn that changeover key, our first valve is locked in the open position. So nobody can come back through and unintentionally close it. Should be a short enough turn that I can get it. Again, this enforces complete valve operation, because if you don't completely open or completely close your valve, you won't be able to withdraw this key. Now that I have closed this valve on camera for everyone, I know it looked very elegant. I can take this key and I can return it to the key cabinet. Now with this one key sitting in my key cabinet, I can prove the position of this valve and all the valves in between. So what this makes it is a very effective way to not only lock your valves in the right position, but you can also know the position of those valves without sending somebody out to physically check. You don't have to worry about a car seal program. and it's a permanent, very robust mechanism. So it is, for all intents and purposes, tamper-proof. So you're welcome to turn off that camera and just look at your screen. Any questions before I go on how that works in a sequence? Or any other questions about those live models?
Right, no questions in the chat so far.
Okay, great. So if you look back to the slide, you can see a little cutaway. And this is why captive key interlocks by Sofis are different than any other product on the market. So internally, inside that yellow box, we have a sophisticated counting mechanism that utilizes a Geneva gear. Without getting into some patent issues, what this essentially does is it counts the number of turns as a valve proceeds into the open or closed position. So as you may have noticed, as I was forcefully turning that multi-turn valve, I could not retrieve either key until I'd reached the end of travel one way or the other. So as that counting mechanism spins, as the valve stem goes up or down, it's holding a locking arm in place. Once you reach the end of travel, the locking arm swings out and you're able to release the key, which then takes you to the next valve. This is all fitted precisely onto each valve. So you see the nut and the lock adapter there. That interacts with the drive form. And this is why we consider our captive key interlocks to be a precise piece of engineering, not a commodity item.
Hey, Jenny, real quick, there was a question that Bert already answered, but I'll let you chime in. The question was, can you retrofit existing valves to use this, or do you need a new valve? And Bert chimed in with, we could do a new valve, we could do a retrofit. I don't know if you want to add anything to that.
Yeah, I'll go ahead and add something to that. These are almost designed to be retrofit because we do need an existing valve in order to get those dimensions. I'll go back to this slide. So the anchor and adapter kits are easily retrofit to any size valve. If you noticed, I don't know if the video is still running, but these are fit on very securely. This one is actually a poor demo. So having an existing valve is almost desirable as long as you can get those precise measurements from the TopWorks.
Very good.
Okay, I'm going to show this little video just because I think it gives a good visual, if you don't already have one, of how this works in the field. So this is showing how both a quarter turn and a multi-turn are mounted. Here's that key cabinet I was referencing. So again, like I showed you, you take that start key, it guides you to the exact position on the exact valve. It must match up. There are no duplicate keys within systems, so there's no chance of mixing them up. And here's our pressure safety valve switchover. So you have to take PSV-B and put it online before you take PSV-A off for maintenance. So again, you take your start key and you place it into a valve or into the interlock, and you open that first valve. All valves were locked into position before this start key was introduced. Now you take your switchover key, close inlet B, and then finally, again, you retrieve that red key, and that red key goes back to your control room so that one, nobody can change the sequence of valves until it is appropriate to do so, and two, you have a real-time update. Okay, so again, this slide just drives the point home further. You take the key from a controlled position, you put it into a valve to render it operable. Once that valve has been operated, you can then go to the next in the sequence, and then the next, and finally back to the cabinet. We use colored and labeled tags. We can put up to 5 lines of labeling on those keys. And then finally, the piece that ties it all together and really takes your safety to the next level is our key cabinet capabilities. Now, this is something that may not have its own IPL rating yet, but this is how we design our keys to be used as a complete system. Again, not just a piece of hardware that you put on to annoy your operators. With our key cabinets, we have sort of 3 levels. So we have a basic mechanical key cabinet where you simply insert the key into the right slot, and you have those keys just visible and neatly contained. The next thing we can do is an electronic key cabinet, which is where you can use your digital control system to control the release of keys for those sequences. So the starter keys, again, that unlock all the valves or lock them conversely. And finally, we have our smart key management. This is a standalone system where we can show updates of each process that is controlled by captive key. And it provides timestamping and identification of who took those starter keys, when those end keys were returned, and requires updates based on your system parameters. Our key cabinets are almost completely bespoke, so this is very tailored to the needs of each individual site. And Equinor and VTTI are our early adopters. Equinor especially has been a big proponent of these and a big force in driving our innovation. Okay, so that's what captive keys are, how they work in a system. Are there any questions I've missed in the chat?
There was one question that I'm going to talk about when I get into the LOPA analysis, but Narsinga asked, what is the difference between captive key versus a manual valve that has open and closed limit switches with lockout options? And I assume that that lockout would be done by some sort of logic solver system.
That is a great question, and I'm really glad that that was asked. So the difference is that lockout tagout is intended for and functions best if you're using it for energy isolation. However, not every procedure that requires exact sequential operation of valves has to do with energy isolation. We can all agree that lockout tagout is used, you have tags as well as locks, so it can get quite cumbersome. And additionally, limit switches are somewhat fallible. They work based on a switch, not a mechanical counting mechanism. So because our mechanical counting mechanisms are, again, I'm going to point to the mechanical or the live demos here, they're all the way back here in the guts of this stainless steel lock body. So they are protected from the elements. They are much more maintenance free, and you don't have to rely on a switch working. And again, the second part of that is you have these keys that are intended to be used as a part of operations, not as a special lockout tagout procedure. So I hope that answers the question. If not, I'm happy to talk about it later. But I guess I'll keep going.
Sure.
Great. So I'm going to walk you guys through some of the common applications that we see. First and foremost, like we showed you in the video, we use this for pressure relief protection. You want to make sure that you always have a way for that pressure to find its way to the outside, and captive keys are a cost-effective and efficient way to do that. So here's an example. Ethylene regen, ethylene treaters, heat exchangers. I showed you that example, PHA, at the very beginning. This is a good example of how Sofis captive keys can be used to tackle the process safety challenges of more complicated, nonlinear processes. So we use sequence control units and a number of other mechanisms so that you can do those depressurization steps. But this is a very effective way and a very cost-effective way to make sure that your pipe specs always line up, to make sure that nobody opens that wrong valve at the wrong time. The next thing that we see frequently is pump startup and control. This can be an operational win as well as a safety win when you prevent deadheading and make sure that your pumps are isolated correctly. The next and newest application that we're seeing is captive keys as a replacement for car sale programs. And here I'm just showing that infamous screen cap from the explosion at Freeport LNG. That CSB report is still coming out, but TxDOT, I think, and OSHA listed car seal programs as a root cause factor. And Freeport is not alone in this. There's been several instances. There was another one in 2019 up in Pennsylvania where a car seal was traced as a root cause. But car seals have two major weak points. And the first weak point is that they are easy to cut, they fall off. They just aren't permanently mounted on a valve. They are vulnerable to either the elements or operator mistakes or both. And then their second point of weakness is their reliance on operators to go out and check that they are in the right position. So even if you have a great car seal program and you have the best operators in the world, we're all humans and we all make mistakes. And if you're relying on operators to go out and see that the valve is in the correct position every single time, it's really just an accident waiting to happen. However, with captive keys, as we have proven now, with one key, you can know the position of almost unlimited valves in a sequence. So instead of keeping car seals on your valves, if you replace that with a captive key program, you not only have a more permanent solution that is weatherproof, tamper-proof, but you also eliminate the need for operators to go out and physically check the position of those valves. Because you have that end key, you've now proven the position of all the valves in that sequence.
Jenny,
and that, yes.
I got a quick question for you related to car seal replacement, and it's something, and I hate to put you on the spot, but if it's something that's not available yet, we definitely as an industry need to have it. So at Connexus, we're in the business of safety instrumented systems, so we deal with a lot of shutdown equipment. And that usually, the shutdown systems usually have a valve as a final element to stop, move to the safe position. What we noticed is that in some cases, not all cases, these shutoff valves are going to be equipped with a manual hand wheel so that you can engage the hand wheel and move the valve open or move the valve closed. So you're basically taking away its automatic functionality and then manually moving it into whatever position you want. Well, if you engage the hand wheel, you've effectively bypassed your shutdown system. So do you have any experience with putting these types of captive key systems on the manual operators of valves that are also automatically actuated? So you've got that manual hand wheel that's going to take effect when you engage it, but we don't want people to be able to engage it without really controlling it. And right now, the only way to deal with that is a kind of a half-hearted car seal program that's more of a tag even than a car seal.
So the short answer is yes. We are able to use pressure permissive and other electric integration. We can integrate our captive keys into automated valves.
Okay.
It's not something that is common, which is why it's not got its own slide, but it is absolutely something that we've done in the past and are capable of doing.
All right, well, we'll have to talk about that offline because I have a customer that I just made a recommendation to about car sealing their manual operators on their shutoff valves.
Yeah. This is my take from the literature I've been reading and attending these process safety seminars and conferences, but I do think that car seals are going to be the thing of the past. There's just no more room for error. And in countries outside of the US, especially on things like pipelines, we've seen captive keys used more for that valve position locking because of their tamper-proof abilities or capabilities. But yeah, that's something that we'll have to talk about after the fact and Again, if anybody on this call has questions or you want to ask what about this, what about that, my information should be available and we will be happy to discuss. Okay, the next application that I like to show people, tell people about is pig launchers and pig receivers. This is a huge application for us in the offshore and pipeline worlds. And this is very important to keep your personnel safe from those high pressures. And again, an example of a non-sequential or non-linear sequential application. So what I mean by that is that there's a depressurization step. So don't think that just because your procedure is not strictly open valve A, closed valve B, open valve C, that you can't use captive keys. It's a very versatile tool. And then finally, I like to just touch on what I term niche applications, just because these are applications that don't usually get the high priority PHA. They don't necessarily have high temperatures or high pressures, but there's still either a lot of value in keeping your chemicals safe, your product pure. And so what I mean here is barrier management for critical valves. We use this to prevent contamination, which Citgo would have really benefited from. I don't know if we have any Floridians on the call, but there was an incident just yesterday, I believe, with a contaminated fuel issue coming out of the Tampa tank terminals. And I don't know what the root cause was, but I suspect that captive keys could have prevented it. In tank farms, these are a very cost-effective way to eliminate spills and contamination, to ensure that only the right valve is opened at the right time. There's a number of different applications there in tank farms. Specialty processing and small batch operations where product purity is critical to either the bottom line or safety or both really benefit from captive keys. There's a very effective return on investment argument to be made there. And finally, filling and loading operations. And so that's what this picture is from. This is from a CSV report on a filling operation gone bad. Somebody used the wrong key because all of these fittings were identical, and they loaded sulfuric acid into the caustic and caused a lot of harm. Keeping flare lines open, guaranteeing that 2 out of 3 instruments are online, aiming absorbers. I could go on and on. There's many different special cases that could benefit from captive keys. And I'd just like to encourage people to think about it. Okay, so
Jenny.
You have been sold on captive keys. You want to know how to get some.
I think someone has a question.
Yeah,
Did
I
someone?
do.
Yeah,
It's
thank
Chris.
you.
I work for Connecticut. I work for Ed.
Okay.
I have a question. Have you guys seen any implementation of captive key on delayed coking units where valve sequential or operation of the valves is extremely critical, where you got 2 coke drums and you don't want to have the right drum, wrong valve, or right valve, wrong drum?
Yes. The answer is yes. We do many coking operations. I know I've seen 3 or 4 projects in the last 12 months or so. So it is a common application. And I should probably make a slide for it.
I
Thank you for
think that
asking.
would be very advantageous. This seems to.
Well, yeah, and the thing that becomes problematic when trying to create a comprehensive slide deck for this kind of product is its versatility.
Right.
We see applications in the municipal water industry, wastewater, some applications in nuclear and power, certainly coking units, but anywhere that there's valves and you need to operate them in a certain order, we are involved.
So this would definitely seem to be a lower cost safety implementation, seeing as and Ed's probably going to talk about LOPA, but we're seeing a 0.01 probability of failure on demand, as opposed to a very complex system of sensors and logic solvers that would prohibit the valves from opening and closing.
Yes, that's right. So I'll go ahead and touch on the implementation procedure, and then I guess I can turn it back over to Ed.
Okay.
So again, I'm sure everybody's read my 6 bullet points here, but I do want to point out that steps 3 and 4 are where Sofis is, again, a highly engineered product and different to almost every other valve control on the market. We need a precise survey of the valve so that we can fit our locking mechanism onto the valve. It's not rocket science. It's not exactly watchmaking, but it's close to watchmaking, not rocket science. So this precise manufacturing is what allows us to have that 0.01 PFD. And number 5, again, is also essential for claiming that credit or that IPL rating. Without the correct installation and setting of our mechanisms, we cannot guarantee a 0.01 PFD. And depending on your policy, you may not be able to claim that 2 independent layers of protection. However, we have many partners all over the US and South America, Canada, who are all highly skilled, highly knowledgeable, and capable of getting people to your site to perform that installation. So with that, I think I'll go ahead and turn it back over to Ed.
Thank you very much. That was very illuminating. This is, again, the captive keys are something that I ran into early in my career. There was a situation where if a company was pumping jet fuel through the wrong pipeline, it would get contaminated, and the jet fuel quality was such that it would cause the flame out of the jet. Can you imagine? Flame out of all of the engines of the plane that you're on. And obviously the SIL requirements were very high, and I recommended a captive key system there because, well, basically, failure is not an option. And what I'm going to show when I get into the layer of protection analysis is that failures generally can't happen. All right, let me go ahead and share my screen. And you'll see that I jump around a lot when I'm giving presentations. I've got several things. So let me begin by just going. Yeah.
Let me show my something very quickly here. So
okay.
Everybody can see that?
Yep, absolutely.
Yes. So this is a client of ours, and this is their allowable IPL captive key lockout tagout system 1E-2. So some clients have already incorporated this as a 1 in 100 probability of failure on demand.
Absolutely.
That's all I wanted to show.
Yeah, absolutely. Having this show up in corporate risk tolerance criteria is quite common. All right, so what I want to do now is I want to kind of go over a layer of protection analysis and a risk analysis where a captive key is part of the situation. Let me make this a little bit bigger. So, and this is available from, I think this is a document that was put together by Sofis, and it talks about a PIG receiver. So for those of you that are not familiar, I'm sure most of you are, when you have a pipeline, it's very common that after some amount of operation, you're going to want to send a pigging device or a scraper through your pipeline. The purpose of pigging is multifaceted now. Originally, it was just to provide something kind of almost as fat as the pipeline to just kind of scrape any junk on the outside of the pipeline through to kind of clean the pipeline up. But now our pigs are smart, so they can take all sorts of measurements on wall thickness, corrosion measurements. They can collect a lot of data. So when we're pigging, we're going to take the pig, which is, it's a device that's roughly the same diameter as the inside of the pipeline. And we're going to launch it from one end of the pipeline, and we're going to receive it at the other end of the pipeline. What you're looking at here is a receiver. So let me get my magic pencil out here. And normally the flow is kind of the green line. So basically you see valves that are open and all the equipment to receive the pig is over on the right-hand side of the screen. Now, when we want to receive a pig, we have to be able to get the pig over here. So how do we do that? And if you look at the procedure to receive a pig, is down here. It kind of gives you the steps in a very cursory fashion. If you were writing the operating procedure for your company, I'm sure you would be more elaborate. But basically, the process is we want to open this valve, V4, which is going to kind of give us our pathway into the receiver. Then we're going to want to open V5, which is going to continue that pathway. So now that we have a pathway for the process gas that goes through the receiver, and then the final step, or not the final step, but final for what I'm worried about, is we're going to now close V2. So we opened up an alternate pathway for the gas that goes through the receiver, and we closed the valve that allowed you to bypass the receiver effectively, which is the normal mode of operation. So now all of the gas is flowing through the receiver when it normally does not. And then when the pig gets here, it's going to land itself in the receiver. And then we have a whole other series of steps where we're going to be able to isolate and drain and be able to take the pig out of the receiver. But for right now, I'm focusing on the procedure of receiving the pig. So it's common for us in the process industries to do process hazards analyses of all equipment and all modes of operation. And when you're talking about a pig receiver, when you're talking about basically a lot of the functionality where captive keys are so valuable, you're talking about a batch sequence, and you're talking about a batch sequence that a lot of the steps are done manually. And the reason that they're done manually, there's a variety of reasons. Cost is number one. Having this pig receiving system be fully automated with actuated valves is a gigantic expense for no good reason. But let me continue. Okay, so we have this process that we need to do a PHA on. So now I'm going to go over into the Connexus Integrated Safety Suite, our software that, well, we have a software package for everything, but we're focused today on the Open PHA product, which is what we use to do process hazards analysis studies like HAZOP, What If, LOPA, etc. So I have a pig launcher procedure HAZOP, I'm going to call it. Now, earlier on, Jenny showed you an excerpt of a LOPA that was done for I think it was an ethylene dryer switchover. So what you saw there is very traditional. So if you look at 1.1, that would be a deviation of misdirected flow. So the way HAZOPs work is you're going to have...
Can you enlarge that?
Oh, absolutely, I can. Thank you for reminding me to do that. All right, there we go. Hopefully that's a little bit more visible. I get on a roll and sometimes I need people to remind me. Okay, so misdirected flow is the deviation, and the deviation works as a guide word that is a prompt for thought. So we say, well, is there a way where I can send flow where I don't want it to? And this would be typical of your traditional HAZOP where you're looking at process deviation. So let me go to my deviations. So there would be a deviation is built of a parameter and a guide word. And of course I have them switched. The parameter actually would be flow and the guide word would be other than. So you have process parameters like flow, temperature, pressure, composition, and then you have guide words that kind of explain how that parameter could deviate from what you want it to be, from what you designed your plant to be. So what we're looking at here is misdirected flow means I have a flow, but the flow is going in a direction that I didn't want it to go. So if you look at the consequence, and I'm showing you a consequence indexed PHA worksheet here, the consequence would be inadvertent opening of either valve V10 or V11 while V4 is open. So let's go back and look at this. So if I open this valve or I open this valve while V4 is open, that's a bad thing. How is that a bad thing? Because it's going to result in high pressure natural gas being released to an open drain. That's going to be released to the atmosphere. You have a potential to develop a flammable gas cloud in the area. If it is ignited, you're going to have either a flash fire or a vapor cloud explosion. And if you have a vapor cloud explosion or a flash fire, we could get a single fatality. Now, I showed you this consequence using a traditional HAZOP. But when you're doing a highly manual system, a traditional HAZOP is not your best approach. So a better approach to do a process hazards analysis of this type of manual operation is going to be a procedural HAZOP. So instead of your deviations being related to high pressure, low pressure, high flow, low flow, other than flow, instead of looking at pieces of equipment, you're looking at the procedure itself, and you're looking at steps in the procedure. So for instance, if we were looking at this procedure, you would run through the guide words for each one of these steps in the procedure. So let's say we are on step number 3, where I want to enter key B into valve 5, or let's just say we don't have a captive key interlock system yet. I need to open valve V5. Well, when you're doing your procedural HAZOP, you say, well, okay, what would happen, and let me go through the other guide words. What would happen if I didn't do this step? What would happen if I did more? So let's say I was manually adding reactants. Let's say I manually added more stuff, or I manually added less stuff. I did the wrong action. I only did part of the action. I did the steps out of sequence. So I performed step 5 before I did step 4. What if this step took more time to do or less time to do than I had planned in my procedure? And the information guide word is kind of feedback to the process. So going back to that coker that Chris was talking about, well, what if I opened up the drum before I cooled it off? Because I didn't have information on how high the temperature in the coker was before I manually opened the valve. So what you're looking at here in terms of a procedural HAZOP would actually be a much better way to analyze this scenario, and a lot of other highly kind of batch manual operations where you're doing a lot of steps in sequence to perform an action. So ultimately, if we were on step 3, we would go to the deviation of other action. So I was supposed to open valve V5, but instead I opened V10 or I opened V11. Ultimately, you see that we end up analyzing everything almost exactly the same way. You get the same consequence. It's going to have the same causes and safeguards and so on. It's just that the deviation is the mental cue that gets you thinking about what can go wrong. And when you're doing a manual process, a procedural HAZOP, probably a better way to do that. Okay, so let's continue on. We've got our consequence and we've got the cause is I inadvertently opened it during the pig receiving sequence. I will get into these numbers down here in just a second. And then you would ask the team, well, what safeguards are in place? And let's say we don't have a captive key interlock system yet. You could say, well, I've got procedures and training. I've got an ignition control program that's going to minimize the probability of igniting the release. The area is minimally occupied during pig receiving, and I've got personnel protective equipment. Now you'll see on the safeguards tab here, none of these are considered independent protection layers, because independent protection layers require a lot more rigorous analysis, which we'll get to in a second. Now, in terms of safety severity, we said that there's a single fatality possible. That's high in our risk tolerance criteria. We said that the probability of this entire scenario happening is low, but because the safety severity is high, that's going to trigger a layer of protection analysis. So a lot of people, when they go from HAZOP into LOPA, there's either a overall risk trigger that moves you into LOPA, or there's a severity of consequence that triggers you into LOPA. So you'll see in our PHA, there's a recommendation that says we should perform a layer of protection analysis because of the high consequence of the hazard. Now, in Open PHA, we can simply now click over to LOPA worksheets and do the layer of protection analysis. So we're doing the LOPA now, and a lot of the information has already been carried over. So the deviation carried over, the consequence carried over, the cause carried over. Now, the first thing we need to do when we're looking at a LOPA, now things are in a little bit more detail, because instead of using qualitative judgment of the team to say high, medium, or low, we're going to start putting numbers on things. We're going to start putting numbers on the frequency at which the failure occurs and the probability of failure of the equipment. And furthermore, we have numerical targets. This is an explicit LOPA, which uses numerical targets to determine what frequency is that type of event acceptable. So if I go over here to risk criteria, and I look at my consequence tables, I'll see that event with a single fatality is only tolerable at a 1 in 10,000 chance per year frequency. So these numbers are going to come from your corporate risk tolerance criteria. Using a 1 in 10,000 for a single fatality event is extremely common in the chemical process industries. Okay, so this is the target. We cannot allow this scenario to occur more frequently than this. And then we're going to use our LOPA math to figure out how frequently is it going to occur. So we look at the initiating event, which is inadvertent opening of the valve. And inadvertent opening of the valve is a human error. So how I came up with this frequency, let me jump out of here and go into my PowerPoint slides. This is the Connexus LOPA facilitator training class. I'm not going to show you. I can't show you the whole class, obviously. But here's a quick section on human errors as initiating event. So human error is expressed as a probability that somebody will make a mistake. And that probability is going to be based on the amount of training they have, human factors, usage of procedures and checklists, the complexity of the task, and so on. But furthermore, you're also concerned about how often you perform the task. The more often you perform a task, the more likely you are to do it incorrectly. So what we need to do is determine a probability that someone will do something wrong and then multiply by the frequency at which that task occurs. So out of the Connexus SIS Engineering Handbook, and you could get similar data here in the guidelines for initiating events and IPLs that we talked about earlier, the book from CCPS. But it's common for if an operator is expected to execute a task, it's part of a procedure they've been trained and qualified for, they're unstressed and not fatigued. 1 times 10 to the minus 3 is an appropriate probability of failure for that opportunity. Okay, and don't forget, don't take numbers out of handbooks blindly. Consider the situation and other factors that might make them perform the task or fail at the task more frequently. If you need more information on human error probability, I highly recommend this book, Human Reliability and Safety Analysis from Gertman and Blackman. But let's go back to our LOPA. And we said, okay, well, the probability that they move the wrong valve when they're in this step is going to be about 10 to the minus 3, 0.001. but we do a monthly pigging. So I'm going to get 12 opportunities per year to get it wrong. And I'm going to multiply that by the 0.001 probability of getting it wrong per opportunity to get myself a frequency of 0.012. Then we look at independent protection layers. And when we looked at independent protection layers, going back to the LOPA, well, procedures and training are not an independent protection layer because they inform your frequency of getting it wrong. Ignition control program is not really an IPL, but it's going to factor into something that we call a conditional modifier or probability of ignition, which we'll get into in just a second. Occupancy is, again, a conditional modifier we'll get into. And personal protective equipment is just kind of a throwaway that you will put into your HAZOP to acknowledge that it exists. But when we're doing this detailed LOPA quantitative analysis, it doesn't really help us. Okay, so we said that we have a frequency of 0.012, and then we look at conditional modifiers, which are things that will prevent the ultimate consequence from occurring, given that a loss of containment has already occurred. It's a situation as opposed to a piece of equipment. So in this case, the HAZOP talked about ignition control, and it also talked about probability of occupancy. Well, in terms of probability of occupancy, there is an operator out there 100% of the time when this procedure is being executed. Maybe there's not 10 people, but there's one. So the area is always occupied. So we said the probability of occupancy is 100% given. Probability of ignition is a very complex. I could spend a half day talking about estimating probability of ignition. But if you go into some books from or some guidelines from the UK Health and Safety Executive in terms of offshore relief statistics, when you release a large quantity of a vapor, a good number to use for probability of ignition is going to be 30%, even if you've got all of the correct electrical ratings of your equipment. Okay, so and I'm going to just bear with me for a second. I'm going to say that our captive key system doesn't exist, meaning its probability of failure is 1.0. Ignore it, pretend it's not there. Okay, so if I just looked at this frequency and this probability of ignition, I have no captive key system. I'm calculating that I'm going to get an event at 3.6 E minus 3 when my target is 1 E minus 4. So my actual frequency is higher than my target. That's no good. I need to do something to decrease the risk of this scenario. Furthermore, that situation or that safeguard needs to achieve a risk reduction factor of 36, which is, for those of you that are familiar with IEC 61511, that's going to be kind of in the middle of SIL 1 range. It's higher than a BPCS interlock, which will give you 10, but it's not quite up to the SIL 2 level, which would be a risk reduction factor of 100. If you invert that risk reduction factor, you'll see a number of 2.77 E minus 2. So if you want to look at probability of failure instead of risk reduction factor. So if you were doing the LOPA of this scenario, you would see that just relying on operator training and procedures is not going to make risk tolerable for this scenario. I need something else. I need something better to decrease the risk of this scenario. So, hey, why don't we put in a captive key interlock system? And furthermore, if you're working with Connexus's open PHA software, you can pull that out of a library. So if I go into the Connexus standard library, I see that captive key interlock system is already in the library. And you saw earlier where Chris showed you some tables from an operating company for their LOPA procedure. So you can create a custom library for your company. So let's say, I don't have a custom library available to me right now, but you could put in all of the typical safeguards that you use, including all the ones that are in the CCPS guidebook, and they're available for you to bring in, which I already did. So I'm going to put the library value of 0.1 in there. So let me update my reference. And if you'll bear with me for a second. Okay, see, I messed around with it, and now it says that what I have doesn't match what's in the library because I made changes to it. But if I could, let me just bring another one down just to show you how that works. So I'm going to bring in a captive key from the library. I'm going to import as new, and you'll see that it brought down my library value. Now let's look, before I kind of give you the big picture, let's look at the captive key interlock in a little bit more detail in our, bear with me for a second, our LOPA training class. So in our LOPA training class, we have a section where we look at the wide variety of potential interlocks or potential independent protection layers and give you more information about them. So here's the information out of our training class about captive key systems, which provides a little bit of information about how they operate. Obviously not the live demo that Ginny gave us, but it's a mechanical system that's going to prevent movement of a device unless the key is inserted. And once you remove the device, move it into its position, you can't move it with the key not in there. It's enforcing sequences of manual operation. And what it does is it prevents an initiating event. That specific initiating event is inadvertent valve operation. It's going to prevent that initiating event from occurring. Now, considerations. Just because you have something doesn't mean you can take credit for it. So number one, when you're going to consider captive key systems as an IPL, it needs to be as a countermeasure to operator error. So it's not going to correct something that's already gone wrong. It's going to prevent an operator from doing it in the first place. So once the valve's already open, it's not going to slam it shut. It's going to prevent you opening it in the first place. Number two, the captive key system has been designed specifically to prevent the scenario under consideration. So if we had, let me go back to here. So if we had a captive key system, but it didn't include the drain valves for some reason that I can't comprehend, then the system wouldn't work. You couldn't take credit for it. So you need to make sure that your captive key system is specifically designed to prevent the scenario that you have under consideration. And then, as Ginny already alluded to, the installation of the system needs to be validated to make sure that it operates properly. And I would agree that you should probably get the manufacturer involved in the installation and commissioning and validation process to make sure that the system works as it's supposed to. Now, so those are the considerations of when am I allowed to take credit for it. Beyond that, we have an effectiveness. So in terms of independent protection layers, we're looking at the probability of failure on demand. We have a baseline effectiveness of 0.01. That's what the fine folks at CCPS said. We at Conexus also publish our own data for the effectiveness of captive key systems, and we will give you a range of 0.01 to 0.001. There are some of our customers have even gone so far as to say that opening a valve in a contradiction to a captive key system is not even credible. So we're not even going to analyze the risk. We're not going to do a LOPA because the probability of a captive key system failure is so ridiculously remote. We're not even going to analyze the risk. We're just basically going to say it doesn't exist. But 0.01, I will tell you, is very conservative. In reality, the only way that a captive key system will not work is, number one, if it was not installed correctly. And if it wasn't installed correctly, you probably couldn't get through the beginning of your sequence in the first place. But the other mechanism is somebody deliberately disables it. somebody has to physically break the system in order to move a valve when it's not supposed to be moved. And I would say that a 0.01, 2 orders of magnitude of risk reduction is very conservative. I wouldn't blink an eye if you gave it a 10 to the -3 or 3 orders of magnitude of risk reduction. But again, you know, when we're doing our risk analyses, we tend to be conservative. And if we get the answer that we're looking for with our conservative number, we don't fight it. We just move on and go to whatever the next problem is.
Hey, Ed,
So
we have a question come into the chat here.
Yeah, so I'm assuming you mean that multiple tankers are going to be unloading into one tank at the same time.
Okay,
There was a question about unloading multiple tankers into one bulk tank at the same time.
Wow, that one is a usage question that is out of my knowledge set. So you would use captive keys. There would be multiple valves and pipe sets that would allow you to offload into the same piece of equipment.
Yeah, so that would be a complicated one, and we'd probably have to integrate our key cabinet pretty heavily there. But I do think it would be possible. If you have, say, 3 inlets into the same tank, I would probably give each inlet its own system and have a local key cabinet. And so when tanker A rolls up, you say, here, tanker A, we'll open valve inlet system number 1. And tanker B gets valve inlet system number 2. But you would need to integrate the key cabinet in order to make sure that you know how each valve system is flowing into that tank. Of course, you would want to have some flow control in the tank so you know the level, things like that. But it can be done.
Absolutely. That's exactly what I was thinking, is that you'd need one captive key system for each pathway into the tank.
Yeah.
Okay.
But I assume that I'm understanding that question correctly. That's also out of my my personal wheelhouse, but I do know that we've done different things at tank terminals, and I've heard my colleagues talk about their projects. So when it comes to valves that are meant to be opened effectively at the same time, so what I mean is that they don't all need to be opened simultaneously, but you need 4 or 5 valves open at the same time, or you need to make sure that a set of 5 valves downstream from another valve stay closed. Whatever the case is, you just pick an order arbitrarily if there's no assigned order, and then we interlock them that way. That's the simplest way to do it. But if I don't understand your question correctly, or if you want more details, of course, reach out.
Excellent. All right, well, let me wrap this up because we're pretty much done. So you saw that I put the captive key system in as an interlock, and I assigned a PFD of 0.01, basically because that's what was in the library. But I also kind of explained why that number is in the library, and the fact that it's actually a very conservative number. Your system is actually probably going to give you better performance than 0.01, but we will conservatively go with that number. So when I do that, you'll see now that my required risk reduction factor is 0. I don't have, these numbers are not red, which means I have met my tolerable risk target. So I needed to get to a frequency of 1E minus 4, and I got to a frequency of 3.6E minus 5. So where did that frequency come from? I take the frequency of the cause, I multiply by the probability of failure of the protection layers, then I multiply by the probabilities of the conditional modifiers, and after I do that, I get a frequency of 3.6E minus 5 is estimated versus 1E minus 4 is target. So at this point in time, the risk of my scenario, the tolerable risk of my scenario has been achieved, and I can go forward saying that I'm going to take credit for this. Once you have taken credit for this, I go into my safeguard list, and you'll see that I created this extra one that I can delete now. You know that when you're done with your PHA, that all of the interlocks, the IPLs that you took credit for, so let me filter the list down to only show our independent protection layers. You know that when you're done with your layer of protection analysis, that this system needs to have a mechanical integrity program. So we can take credit for it as long as we give it the attention that it needs. So I don't know, Ginny, I'll let you jump in here in a second, but what I expect is a mechanical integrity program that would be occurring at roughly a turnaround interval and be nothing more than a visual inspection to check for signs of wear and tear and or disablement. Do you have any commentary on mechanical integrity program to make sure that this system is effective over its entire life cycle?
Yes, I do. So I am going to hop back on camera here.
All right.
Just to point out a couple of things. So
let me close out of my screen share so that everyone can see that.
As far as lifetime mechanical integrity, we have records of these guys lasting 20 years in the right conditions with a little bit of TLC. So I want to point out, again, it's easier to see in real life, but we have a little piece of metal that blocks entry into the lock body when you don't have a key in there. And most of the time you will only have one key in a dual key lock. We do also have single key locks, but that's another conversation. So your one key is stuck, your valve is locked. Everything is stainless steel components, so it's very, very robust, almost maintenance free. Here's what we do recommend. Number one, we recommend that you have these properly installed by a certified Sofis representative or Sofis technician. That is critical. Number two, from time to time on multi-rotation locks or multi-turn locks especially in dirty or corrosive service, you may notice that that seat position is going to change, either due to wear or due to buildup. What this will do is it will change the set position inside the lock. So if you recall, when we operate our valve using a captive interlock, it's important that we have that position, right? Because if I rotate this valve or open this valve, excuse me, and my seat position has changed. So perhaps it was 17 turns originally to fully open this valve or to fully close it, but now there's buildup. So I get to 15 turns and it's closed. My key is not going to come out because the lock has been set for 17 turns. This is not a super common problem, but what this means is that you put your interlock on your valve PM schedule. So if you are PMing your valve because it's in a dirty service and it gets buildup, put your interlock on the same schedule. So as you start to notice that buildup, there's a very simple reset procedure. We recommend that you either get a Sofis technician to work with you or a Sofis representative to work with you. We provide service packages where you can, it's essentially worry-free. We'll come out and we'll do an inspection every year, every 3 years, and take care of that. We also offer training so that you can do it yourself. But if you don't get that position reset, you're not going to be able to put your keys in or withdraw them the way you used to be able to because you have wear to the valve. So that's really the only PM that we recommend. Other than that, if you have these set up all over your site, it's probably a good idea to have a complete survey, maybe every 5 years. And again, get a certified Sofis tech or a certified Sofis representative to come out and simply take a look at your valves. Make sure that these nameplates are still secured. Make sure that everything is working the way it should be. Really, it has to do with your valve and your site. So if you have valves that wear out pretty regularly, every 1 to 3 years, then put your interlocks on that same PM. If your valves are in clean service and they are lasting for 5, 10 years, hey, it's pretty worry-free in that case. Does that answer your question?
Absolutely. That's that's what we're looking for. We want to make sure one of the problems in the process industries is something gets installed and everyone has good intentions, and 20 years later, 10 years later, it's never been tested, it's never been maintained, and it won't work if we had to.
Yeah. So make
right.
sure that you're operating your valves routinely. That's kind of our standard line. If there's no other information given, operate your valves once a year and make sure your captive keys are working at the same time because they fit together. Hope that answers it.
All right, very good. Thank you. And with that, that's pretty much all that I've got. That was a comprehensive discussion, I would like to say, of a very valuable and underutilized independent protection layer, both in terms of what it is, how it works, and then how we do that process hazards analysis in LOPA. And with that, I will turn things over to Chris to kind of see if anyone has any remaining questions and wrap things up.
Does anybody else have anything?
Okay, well, let me just kind of jump out here while people are kind of winding up any questions that they have. Thank you very much for your time and your attendance. We appreciate your attendance at these. I think it's a very valuable source of information. I hope you like the format. I want to do this more frequently. As a matter of fact, I think that it'll probably be a few months, but I think we're going to want to invite Jenny back to talk about another product of theirs, which is the remote actuator. So they have a product that allows you to turn a valve from, I don't know, 30, 40, 50 feet away, which for those of you...
Ed,
yeah.
It's actually 90 meters.
90 meters.
Sorry, 90 feet, 30 meters. What's a kilometer? I'm American.
So there will be a discussion coming up about API 553 and the need to emergency isolate valves. So let's say I've got a pump and the pump seal is leaking. You're spilling a large inventory of hydrocarbon. It's on fire. How do I close the valve? Because there's a huge fire around it. And one of the, again, underutilized answers is, well, why don't you just put your hand wheel for the valve 90 meters away where you can close it safely? So I think we're going to want to do that one also in the not too distant future. So that's all I've got. Any other questions? Any other comments from your side, Jenny?
No, I agree that we need to do another webinar. I'm actually working on a paper about exactly that subject and how our Flexi Drive complies with those new regulations. But I do want to say thank you to everyone on the chat, or I'm sorry, thank you to everyone on the call. Thank you for the great questions in the chat. And I hope this was of some value.
Thanks everyone for your interest in joining us today. Thank you, Jenny, for your excellent presentation. Thank you, Ed, as well. I think we'll end today's webinar. And thank you, everyone.
Thanks, everyone.
Thank you, guys.